Okay, after Ampere's law, we're going to extend this to well, what we can do with it. And we're going to talk about the magnetic field of a toroid and a solenoid. Okay. So, we need to review Ampere's law a little bit. You should memorize this, that the integral, closed loop integral of b dot ds equals mu naught I enclosed. Memorize this. This is Ampere's law. Okay, and this is the way. This is the shortcut way of looking at the strength of our magnetic field. Okay, and it helps a lot just because we can't really draw a surface area around our under I, and we don't have to do a whole lot all that math that we did when we derived out of Biot-Savart law. Whew. Okay, so what is a toroid? A toroid, okay, looks like this. Okay, I'm going to draw it kind of big here. Okay, it is a donut-looking thing. All right, and with the donut, we have a wire that wraps around and is looped around our toroid. To the point where we have all these loops of wire going around our toroid. And this is our current coming in equaling our current coming out. Just you guys are on track with what we're going here. You guys following this? All right. So, what we're going to look for first is on the inside here. What's going to be our magnetic field in here? Well, according to this, our magnetic field is related to our I enclosed, right? Well, are we enclosing any loop?
I don't think so. Do we?
There's no current in there. Because there's no current in there, okay, as long as we're inside the whole thing, that b times 2 pi r equals mu naught I enclosed, well, that equals 0, therefore, okay, there is no magnetic field inside the toroid. Okay. Now, here's the odd thing. If we do it outside the toroid, okay, it's the same thing. Because we're not enclosing any particular amount of, we're not creating a loop. Okay, that is encompassing any amount of current. We have current going in, we have current going out, okay, but it's not through the loop. Follow what I'm saying here? This current is not going through the loop. Therefore, outside the toroid, there is no field. Okay, so for inside and outside the toroid, our magnetic field equals 0. However, within the toroid itself, we have something a little different. Each one of these, each loop here, and so we're gonna look at it end to end here. Each one of these has, okay, so this is where we kind of have to get, okay, stick our thumb in the direction of the current. Okay, so that means our magnetic field inside is, what's my, is going that way inside, yeah?
Left.
Think of it more as clockwise. For any particular loop, the field is going to be going in this direction. Inside. Yeah? Okay, if you can twist your arm around the whole time, the current's going to be going in that direction. Okay. So if we're going to draw our enclosure, okay, if that is now our enclosure, okay, then we're going to have, in any particular one of these guys, here's our enclosure. Okay, for any particular one of them, we have fields inside of that going in. So here it's going in, and there 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 it's going in, right? You guys follow me there? And then on the outside, we have dot, 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 dot. On the other side of the enclosure. Yeah? So we have a certain amount of current enclosed. Not only that, but we can quantify how much current that is. Because each time it goes through the center of here, okay, we get to count that as a current. Yeah? You guys following me there? Think of the loops. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 times our current goes inside of our enclosure. And then it leaves the other side. Right? But the current inside our enclosure is always in the same direction. Therefore, for this one in particular, we have 12 loops. Which means that whatever our current is, this is our total current enclosed. So we'll stop for a second there. Try and wrap your head around that. Our solenoid, our toroid, is wrapped with a current, right? Wrapped with a wire that has a current running through it. Okay. Every time it goes into the enclosure, it has current traveling in the same direction. Every single time, it's got current traveling into the page. Every single time it enters the enclosure, right? And so, but if it's every single time, we can count how many times that is, right? So in this particular case, it's 12 times. So our B then times 2 pi r, because we're still traveling in we still have a circular enclosure, is going to equal mu naught times the number of loops that are around our solenoid, our toroid, times the current that's in the wire. And that gives us, we want to take our R out, a magnetic field equals mu naught N I over 2 pi times 1 over R inside the toroid. So however far we move, whatever the radius of this is, okay, if we move out, then it's more current that's inside. You guys see that? Okay, so this, okay, this is our magnetic field inside of a toroid. Okay, now what might this be used for? What's that? Okay, well, if we create this magnetic field inside this toroid, okay, let's imagine this was, oh, say, 5 miles across. What's that? It's a particle accelerator. This is how we make a particle accelerator. It's one giant toroid. Okay, think about the engineering that would take to go into this. Okay, the magnetic field's involved. Okay, and just how freaking huge the Large Hadron Collider, the LHC, is in Geneva. And this is what they're going to use. They're going to accelerate particles using this to hopefully create little black holes and possibly discover empirical evidence of a multidimensional universe.
Black hole
But
over Earth?
we'll pause on that and discuss once we finish the lecture. Okay, so that was a toroid. Now we have, okay, okay, so now we have a solenoid. Okay, solenoid. We'll get to the more colloquial name here in a minute. Nope, because it's not going to be called the colloquial name on the test.
Yeah, colloquial is not really colloquial. Don't you think so? Abbreviation so long. But we made this with Mr. Giravidi and our science class. It gets really hot.
No, he created it here.
Yeah.
What?
All right. So here's our solenoid. Now, in the solenoid, we're going to look at it end on here for a sec. With our solenoid, we have our central material, and then around it, we have. So we're going to look from this direction here. Okay, we'll draw little pretty eyelashes on there. Okay. And I totally ruined it with a jacked up nose. All right. So we're looking from this end, which means our current is coming this way. Yeah? Did I draw that right? No, I drew it from the other side. Sorry.
Oh no.
Should be this way. Okay, so there's our current. Okay, which means if our current's going this way, that means inside this, okay, we have our field is coming up out of the page, and outside outside it's going into the page. Okay. Which really means that we have this huge magnetic field out and coming around. Okay, and it's going to go way out and come back, and way out and come back. And yes, I cross field lines, but deal with it. Okay. So, all right, make sure I got my drawings here right. Okay. So if we're going to try and find B outside of this, we've got all these currents. Okay, so these are the currents on the outside of the wire. All right, and if this is the current, that means it's going to have an electric field going this way, another one going that way, another one going that way, and around and around and around and around and around. But in between any one of them, so we're going to zoom in. In between any two of them, we've got one current going that way, but the other one's going up like that, right? And they're coming from the same. Okay, so if they're next to each other, we have one going in that direction, okay, and it curls around. But when they meet, it's meeting up with the next one that's in the opposite. That's in the opposite direction. And so in between all of them, they cancel each other, but that creates a magnetic field going that way. Right, that all of these wind up pointing in that direction. And same thing on the other side. If the current's coming up, right, this also creates magnetic field going that way. Okay. And that is what creates this huge magnetic field going through our toroid. Right. Well, this only happens when the current is going through it, right? What happens if we turn off the current? We lose the magnetic field, right? Not only that, but if we have more of these loops lined up, okay, the stronger the magnetic field. Okay, this, the colloquial term for this is an electromagnet. Okay, that is scientifically called a solenoid, and there's all kinds of purposes for a solenoid. If you hit the lock or unlock button on your remote, on your keys, sends a momentary electric signal to the magnet that's going to either push up or pull down on your lock inside your car door. Okay, that's a solenoid. Okay, turning the starter. Okay, turning the key in your car starts the solenoid, will get your starter going. Okay, so that is a magnetic field with a solenoid, and the math is the same, you guys. You can probably see that the math is pretty much the same. So that is the magnetic field for a toroid and solenoid. So that's all right, and there you go.